Okay, great. Well, I hope you still have some energy left. I have a little bit. Hopefully, it's going to last for the 1 hour 45 minutes. So, as I promised in answer to your question, let me just say quickly how the state operator map works for the case of the free massless scalar. Oh, great, thanks. So let's consider the free massless scalar in d dimensions. As I told you, the local operators in this case can be listed completely explicitly, and they are shown on the blackboard. So of course there's a scalar itself phi. So phi has dimension d minus 2 over 2. This operator, so we can take derivatives of phi. This operator is going to have a dimension d minus 2 over 2 plus n. And we can take as many derivatives as we want. This is something which is transforming into symmetric representation. You know, these indices are symmetric, so they're. Oh, sorry, this is supposed to be j. Okay, so there's j derivatives which are completely symmetric because they commute each other. So this thing transforms into symmetric representation of spin j of SOD. So when there's some SOD symmetric of rank j. So this is usually, maybe we can write it. V is the fundamental representation, and it's subject to the equation of motion. The equation of motion is that derivative squared partially is 0, which really means that there is only symmetric traceless representation of rank j. Okay, so there is precisely one irreducible representation of SOD for each j, and it's the symmetric traceless representation of SOD. So these are kind of the basic building blocks, and the most general local operator is a normal ordered product of these things. So you can take this to just some normal product of these things, and let's see, how does this match with the counting and energies of states? Okay, we want to consider states on SD minus 1. So we would quantize the theory on SD minus 1 times R, starting from the action, which looks kind of like this. So I guess so we have an integral over. So let's write the Lorentzian action. We have an integral over time, integral over the unit sphere of something like 1/2 dt phi squared. So this is the kinetic term. Then there's the potential energy coming from the transverse derivatives. So this is the sphere Laplacian. So it's the Laplacian on SD minus 1. And then there's actually a mass term because of Weyl anomaly, there is some extra factor here times phi squared. So it turns out if you do a conformal transformation from flat space to the cylinder, then you pick up an extra mass term essentially, which will be important, but don't worry about it for now. Okay, and now we want to quantize it. So we want to write down the quantum operator phi of tau and n. So n is a vector on the unit sphere, and we are supposed to write this so as a sum over all the possible modes, and it's going to look like e to the I the energy. So let me mode I. So I runs over all the possible modes, the energy tau, and some creation operator. Okay, I never know which one is a minus, which one is a plus, but and so annihilation operator, creation operator. And to find, now we need to find the set of possible modes and the corresponding set of energies, which are found by solving the equation of motion, as usual. This is just like free theory, as you know. Except in flat space, we are doing it on a compact manifold, which is the sphere. So the equation of motion are dt squared phi equal. Sorry, so d squared, I guess probably d equal to the Laplacian, the sphere Laplacian, plus this extra number. phi, so equation of motion like that. So to find the modes, we need to diagonalize the Laplacian on the sphere, and the eigenvalues, well, what are the eigenvalues and eigenvectors of the sphere Laplacian? So of, well, you may know the answer to this. I will not really explain why the answer is like this, but this is the answer. So the eigenvalues look as follows. So the eigenvalues are j times j plus d minus 2. So when for example, you can check this. Yeah. So when we are doing sd minus 1 for d equal 2, right? So then it's s1. Then this is just j squared. So these are just the plane. These are just the sines and cosines, which have eigenvalues j squared. And well, what is the multiplicity? Well, the multiplicity is precisely the symmetric traceless representation of SOD of rank j. Right? The multiplicity. So there is a multiplicity or degeneracy where the finite dimensional vector space of eigenvalue of eigenvectors with this eigenvalue is exactly the symmetric traceless of SOD of rank j. So you can see it already starts looking very much like the space of local operators. And now to match also the energy. So what's, yeah. Mm-hmm. This. No, I think it works for d equal 2, right? Set if you set d equal to 2, then we get S1. So S1. Then on S1, the eigenvalues are just squares of integers because the eigenvectors are e to the I j theta, right? Theta is the angle on the sphere. I mean, on S1. So these are the eigenvalues. And when we, well, another check, just set d equal to 3. Then S2. On S2, it's a representation of SO3. Then it's j times j plus 1, which is exactly the Casimirs for SO3. It's basically the Casimir for SOD, this thing. Right, so SOD acts on SD minus 1 in a natural way. Okay, this is the multiplicity. So you can already start seeing that the multiplicity of this eigenvalue with value j is the same thing as the multiplicity of this operator with j indices. And now let's see that the energy matches a scaling dimension. Well, so from here, the energy is the Laplace eigenvalue plus this number, which I'm not now going to tell you finally what it is. Because I didn't have much time to actually prepare this, but now I know this should be this number, which is a complete square. I mean, it's just the square of that, right? So, okay. In other words, we can the creation operators can be labeled as A, J, A, J, M, I guess, where J runs from 0 to infinity, M runs from 0 to the dimension of this representation. So let me just call it Vj. So this is the symmetric traceless of SOD rank J. Okay, so this is the complete set of annihilation and creation operators. Well, sorry, these are the creation operators. Annihilation operators are just the Hermitian conjugates. And the energy on the cylinder of AJM is degenerate. It's just equal to, sorry, Somebody should have corrected me. So, we are solving this equation. So we have energy squared, lambda j plus a constant. So the energy is just d minus 2 over 2 plus j, because this is the energy squared, right? So this this matches exactly what we had over here. That if we insert, so let's imagine inserting this operator at the origin. Okay. Now it creates some state on the sphere, and what is the state? Well, it is the state which is obtained by. Okay, I'm sorry that there are indices a here, but this is the creation operator. Well, it's the state obtained by acting with this creation operator on the vacuum, right? Where this j, capital J, is the same as this j, and the multiplicity exactly reproduces the multiplicity of the derivatives over here, right? And it's okay. Is this clear? No. This is So this is RD, and this lives in the Hilbert space that we discovered by quantizing the theory on this geometry. Right. So what we did is that we took the free scalar. We considered the free scalar on r times sd minus 1. We solved the equation of motion on r sd minus 1 to find the normal modes, as we usually do when we want to find the Fock space for a free theory. Usually we do in a QFT course. You do this in flat space, so the set of modes is infinite, labeled by the spatial momentum. In this case, instead of spatial momentum, we have the discrete set of modes, which are the solutions of the Laplace operator on a compact geometry. So there's a discrete set. And what is the discrete set? Well, it's labeled by two integers. It's labeled by j, which runs from 0 to infinity, and then it's labeled by m, which runs from 1 to the dimension of a certain finite dimensional representation of SOD. And then you can ask, what is the energy? So energy meaning the eigenvalue under the translations of along the cylinder. So this is the time evolution, right? So eigenvalue under that one, that we can recover from the equation of motion, because this is the minus the energy squared, and this is minus lambda plus some constant. And we said lambda is this, so you just plug it in and you solve for the energy. So you find that the energy is that, which is exactly the scaling dimension of that operator. Right, so it's the same as what I wrote here. Okay, was that? Yeah, so I had like 15 minutes to prepare this, so it's still a bit chaotic, but.
So these operators are technically definitions, right?
They are the local operators. What do you mean? They're different. They're part of the theory, but you can also use them to deform. Most of them are irrelevant. Only a handful are relevant. Yeah. But okay. Now notice that not only that we reproduce the energies of the single particle. So these are like the single particle states, right? These are the single particle states. But we also reproduce all of the multi-particle states, because just like we can take normal ordered products of these operators, their scaling dimension is going to be additive. In a similar way, we can just consider states which are obtained by acting with many of these creation operators. and that's just going to correspond to the normal ordered product of a bunch of these guys. So there are as many phi's in the local operator as there are creation operators here. Yeah. Okay, just think about it if it was too fast, but it's really, yeah, it's not too hard. Well, okay, I didn't derive it from first principles. I just I guessed it to guarantee that this is a complete square, that we get the right answer. But there is a way to do it in a more principled way. So in general, the keyword is conformally coupled free scalar. So the conformally coupled free scalar is just the action is like the usual action. Yeah, well, the question is, what does the action look like on a general manifold if you want to preserve conformal invariance? Yeah. Yeah, exactly. There's a Rich's scalar times some number, which, okay, again, I don't remember. It's probably something that has d minus 1 in it. Oh, okay. There's some number here, which depends on d dimension. Now, if you evaluate the Rich's scalar of the d minus 1 sphere, you'll see that it's proportional to d minus 2, right? Because the S1 has 0 Rich's scalar. So yeah, but the cylinder has a sphere in it. So this one comes from SD minus 1 in our case. Is the Rich's scalar SD minus 1. Yeah. Okay, well, that was just to, yeah. Yeah. Yeah, yeah, yes, yeah. So I mean, there's a general property which is a state operator map, which is a property of CFTs, and because my explanation in previous lecture was a little bit maybe unclear and a bit abstract, I wanted to show you a concrete realization, just to show you that it's a very hands-on thing. It's really an explicit map between states and operators in this particular CFT. Yeah. Yep, I guess. Oh, maybe you were first. I don't know. Oh, okay, sorry. I mean, it doesn't matter. I'm going to take both questions anyway. It's fine. Of the what? No, it doesn't. It has to be any local operator, but you can. But yeah, any local operator. Well, the intuition is to do the path integral over the interior of the ball. Okay, I don't. And then that, as we discussed, that creates a state. But, well, I didn't explain it in this detail how it works in this setting. I just showed you the match explicitly. So I give you like a general reasoning about the path integral in a previous lecture. Now I give you a concrete mapping for a free scalar. So yeah, I guess I could also, yeah, I think if you probably go to Polchinski, then you can see how exactly it works for a free scalar, like how my explanation from the previous lecture works for the example of the free scalar. Yeah.
Is the whole surface the state or the impact space where the state?
So SD minus 1 is where the states live. It's not the state. The states are in principle linear functionals of the field on that surface, but in our case we think of them as arising as kind of abstractly as creation operators acting on the vacuum. So for each of these things, there is a particular linear functional acting on functions on SD minus 1. You can find that linear functional in Polchinski. I don't remember it, but yeah, that yeah. Okay. Mm-hmm. This side. Well, yeah, I didn't. It's a property of the Laplace equation. If you solve the Laplace equation on SD minus one, you'll find that the energy levels. I mean, it's the story of spherical harmonics. Mm-hmm. Left here. How does it work here? The counting. The multiplicity is the following. So you have J derivatives. Derivatives commute. So it's a symmetric. So first of all, SOD acts on this index, right? It's an SOD index, a vector representation. So derivative is like a d-dimensional representation of SOD because there's d of them. If you take J such derivatives, it's a symmetric. Is the symmetric Jth power of the fundamental. But now it's traceless because the field satisfies the equation of motion, right? So it looks like a very different reasoning on the two sides. On one side, we are solving the Laplace equation on the sphere. On the other side, we are not solving the Laplace equation on the sphere. We are just counting derivatives and using the equation of motion. But the answer is the same. So it looks quite non-trivial. Mm-hmm. Mm-hmm. Yes. Yeah. Yeah. I mean, well, that's not what I explained, but it's true, I think. Yeah, I think I should probably move on from this example. So, contemplate this example as much as possible, or feel free to ask me questions after the lecture in some other Q&A. But now let's again leave the free scalar in the past and do some more general CFT. So in a general CFT, the Hilbert space is not obtained by acting with creation operators arbitrarily many times, because that's a very special property of the free theory. But in spite of that, we can say a lot about the Hilbert space of a general CFT. So basically, this whole story of the CFT is very much it applies in a strongly coupled setting in a non-perturbative way. Okay, so unitarity. Okay, so we have these generators that we talked about before, P, D, K, and M, and they correspond to. Okay, so now let's think about a Hilbert space. So we have our Hilbert space, which is the vector space that the CFT associates to SD minus one, that we saw for the free scalar just a moment ago. And now let's think of these as operators acting on the Hilbert space. If the theory is unitary, then these operators satisfy certain hermeticity conditions. And now let's discuss what these conditions are. So we are to remember that D became the Hamiltonian, so it should be Hermitian. So D is Hermitian. And well, what is the general? Why do symmetries have to do anything with hermeticity? Well, it's because if you're in a Lorentzian QFT, Lorentzian quantum mechanics, then Wigner explained that any symmetry gives rise to either a unitary or anti-unitary operator. So if you have if you read Weinberg's first book, then it's explained very well. But this is like a general theorem that any symmetry of a quantum theory, quantum field theory, gives rise to a unitary operation, which realizes that symmetry. So we have some symmetry gives rise to some unitary operator. So unitary means u dagger u is 1. And when it comes to space-time symmetries, the space-time symmetries are those which are manifest in Lorentzian signature, so not Euclidean signature. It's important. So Euclidean time translation. So symmetries are manifest in Lorentzian signature. Space-time symmetries. So, for example, Euclidean time translation is not a symmetry. I mean, in a sense of it's not a physical symmetry of the real world, right? In a real world, Euclidean time translation has nothing to do with the real world, so it shouldn't be a symmetry. So, indeed, if you do a Euclidean time translation, it's or it's Hamiltonian if you wish. It's the same thing, right? This is a Euclidean time translation, and it's not a unitary operator because if you do, that, then you get the same thing, which is definitely not its inverse. But if you do a Lorentzian time translation, you put an I here, then the Hermitian conjugation gives you minus I t, and this is indeed inverse of the origin time translation. So that's just to illustrate this general fact. So okay, and now if you have another fact is when you have a continuous group acting like a symmetry, then you want to think of u as an exponential of some parameter times an operator. So if t is a real parameter, okay, so let's imagine that this corresponds to a symmetry, which means that u is unitary. This means that A, or this is equivalent to A being anti-Hermitian. Okay, so just to summarize, Lie group acting as a symmetry corresponds to unitary transformations, and Lie algebra acting as a symmetry corresponds to anti-Hermitian operators. Okay, so now we need to see which of these preserve the Lorentzian cylinder, and those will correspond to anti-Hermitian operators. Okay. So we already saw that D does not correspond to a symmetry, but I times D does. So I times D is anti-Hermitian, or in other words, D is Hermitian. So which of them are symmetries? Maybe the simplest is to. Okay, well, I guess it's kind of obvious that MAB is a rotation, right? So a rotation just rotates the SD minus 1. It doesn't do anything with time, so MAD is a symmetry. So MAD is going to be anti-Hermitian. Then D, well, D is not a symmetry, but ID is a symmetry. So that means that ID is anti-Hermitian. In other words, D is Hermitian. But now we need to think about P and K. This is the slightly non-trivial part. So basically, we consider we need to consider how these generators act on the Lorentzian time on the cylinder. So remember that we have that E tau is equal to x is the absolute value of x. So x, this is the radial quantization. So tau is 1/2 of logarithm of x squared. So the Lorentzian time, sorry, what's the relation between Euclidean time and Lorentzian time? Euclidean time is tau. Lorentzian time is t. So Lorentzian time is 1 over 2I log x squared. Okay. So let's ask ourselves, if we perform a translation, how does a translation change Lorentzian time? So translation, as we said, was minus, I think in my convention it was minus p. I guess it's not gonna matter. So it's this. So when you translate Lorentzian time, it's like acting with derivative on this expression, which is same thing as 1 over I xa over x squared. Okay. And if you do it with the t, then you're going to find, this is an exercise if you wish, you're going to find 1 over I times xa. Okay, and let's rewrite this in terms of the cylinder coordinates. So this is minus I times na e to the minus it, right? Because, okay, is this, if in case it's not clear, then let me know. And this is minus I na e to the it. Right, so remember that xa is na e to the tau, which is the same thing as na e to the I t. So in particular, points on the Lorentzian cylinder, they don't correspond to real values of xa, of course. I mean, it's some complex value of xa, and we are trying to identify which linear combinations of the translation and special conformal transformation preserve that complex locus in CD, right? This is some point in, this is some kind of d-dimensional real subset of d-dimensional complex space. And well, you can see that individually, P and K certainly don't preserve it, because if you act on a real time, you get something complex with both of them. But there's a linear combination which works. So what's the linear combination? Well, the linear combination is PA minus KA. When it acts on T, you get, sorry, you probably get something like minus 2 Na sine T, which is real. And if you act with I times PA plus Ka on T, then you get 2 times cos. Okay, so these two linear combinations of the vector fields, they preserve the Lorentzian cylinder, which means that this is anti-Hermitian and this is anti-Hermitian. So they're both anti-Hermitian, which is the same thing as saying that PA, Hermitian conjugate, is Ka. Okay. So that's the final. Okay, so let me just summarize it. So we have that PA Hermitian conjugate is Ka, D Hermitian conjugate is D, and MAB is anti-Hermitian. Okay. Anyway, so I think this is the right way in general to think about symmetries in QFT. Like often people get confused with eyes and so on. So symmetries never have eyes. That means symmetries are just, you have a real Lie group and a Lie algebra. So it's a real Lie group, a real Lie algebra. There is no eyes anywhere. And when you realize it in a representation, the Lie group should correspond to unitary operators, Lie algebra to anti-Hermitian operators. and you're done. So you never get confused about where to put ice. Well, D is like the Euclidean time translation, which is not a symmetry. Sorry. Yes, yes. Yeah. Hmm? No, well, no. Well, quantum field theory is a special case of quantum mechanics in some sense. It's a quantum mechanics. So Wigner's theorem applies to any quantum mechanics, to any quantum theory, and quantum field theory is a special case of quantum mechanics when your system has continuous number of degrees of freedom. So it also applies in that case. Yeah, so non-invertible symmetries, right? How do they? Yeah, yeah, maybe that's a bit of a distraction. Sorry, non-invertible symmetries. I guess they can't correspond to unitary. Yeah, okay. I'm not sure how they fit in exactly, but anyway, these things are invertible. The transformations, the conformal transformations have inverses. Yeah, maybe you're right. Actually, I would have to think about it carefully. Yeah, sorry. Does anybody know the answer? How do non-invertible symmetries fit in with Wigner's theorem? Yeah, no. It's a good point. It's a good point. I mean, I concede that I don't know what the answer is, though. Yeah, I'll try to answer in the next lecture. I guess the point is that non-invertible symmetries do not from some kind of classical operations. They are somewhat more general. Like the Wigner's theorem is supposed to apply to kind of physical operations that you can do physically with the system. And the assumption, the assumption is that symmetry, an operation that you can do with a system, is an operation which should preserve all the probabilities. So, like all the squares of inner products of states, and then from that you can conclude that they have to be realized as unitary and anti-unitary operators. So, I guess it has to be that non-invertible symmetries are not of this type for some reason. But okay, I don't see why they're not. Yeah. So what was the logic? We were asking which geometric operations preserve the Lorentzian cylinder, because these would be the symmetries. And we saw that P and K individually do not preserve the Lorentzian cylinder, but these linear combinations do, because when we act on time, you get something real. I didn't show that they also preserve the in the angular coordinate, but it's true. So these two things are vector fields, which are symmetries to the Lorentzian theory, and therefore their exponentials are unitary operators, and therefore they themselves are anti-Hermitian. And from this being anti-Hermitian and this being anti-Hermitian is equivalent to P A dagger being Ka. Okay.
Sorry, but why does that help? The fact that PA dagger is KA.
Well, we want to know how. So Good, that's good. I should have said a few more things. So in general, classifying representations is hard, but classifying unitary representations is it's a much more constrained problem. So for now, we just know that local operators are a representation of this conformal algebra of SO1, d plus 1, but we don't know what kind of representation. And the answer is it has to be a unitary representation. So it's a vector space with an inner product. And to make the next step, we need to know how these conformal generators play along with this inner product. In other words, what are their hermeneutic properties? So, and we just found them. So now we are going to use it to classify the kind of representations which appear, which the local operators fall into. Okay, so well, I could also say that, let me just list all the anti-Hermitian operators, just for the sake of it. So this is the Lie algebra of symmetries. They are MA, ID, and PA plus KA, and finally PA minus KA. And these form the Lie algebra, which is SO2, D. Okay, so in fact the group which acts on Lorentzian cylinder is this one, is SO2, D. It's not SO1, D plus 1. And therefore the anti-Hermitian generators correspond to this Lie algebra. You can again check it. So it's not SO1, D plus 1, but it's SO2, D now. Okay, very good. So now we have the Hilbert space V of local operators, and it's a unitary representation of this algebra. By the way, well, there is an obvious SO2 times SOD subgroup. So SOD just corresponds to rotations, and SO2 at the level of the algebra is just R, right? There is no difference between SO2 and R. So that's just the time translations. Okay, so and then this one and this one, they live in the off-diagonal pieces of SO2. Yeah, maybe I should, let me draw it again. So we have this picture now, SO2 times SOD. This is, it's the same picture as before. It's just that now this is 2 and this is D. This is M. This is D, or minus ID. I don't know. I guess ID. And here we have P and K mixed up in some way. Okay. Okay, very good. So once you're in such a situation where you have a unitary representation of some Lie group, you want to decompose it into irreducible representation. Right? This is how we talk about particles in quantum field theory, where particles are just correspond to unitary irreducible representations of the Poincare group. In this case, we have more symmetry, more than Poincare. We have the whole conformal group. So we want to decompose V into irreducibles as a direct sum. So this is some irreducible representation. So now, what are the possible irreducible representations? Well, you see. So we can always work in a basis where D is diagonal. And D is the Hamiltonian. So remember that usually in quantum theory, energy should be bounded from below. So this thing should be bounded by some number. Let's call it E0, right? The energy of the vacuum. And remember that when we act with K, so K, sorry, yeah, the other way. So K is like a lowering operator for the energy. So K lowers the energy by 1. Oh, did I write it the same again? Oh. Okay, D, like this. D on K is minus K. Right? So K is a lowering operator for the energy. K lowers the energy or scaling dimension. So energy is the same as scaling dimension by 1. And conversely, the P is like a raising operator because D acts on it with a plus sign. So P increases the energy by 1. But since our energy is bounded from below, at some point the K will have to annihilate our state. Otherwise, if it keeps going, it will generate states of arbitrarily low energy. So that's not allowed. So K, I mean, if you're in an irreducible representation, let's consider the subspace. The subspace of this irreducible representation, which is annihilated by K. So we have some, let's just write it like that. Okay. Now, these O's are their representation of D, so meaning that D acts like some scaling dimension. And also the O's have to, okay, so let's say there's a bunch of them. And the O's transform irreducibly under rotations. So under M. Okay. Then I can generate all of the other states by acting with the raising operator. So the picture of the irreducible representation is like this. Now it's some linear span of this OA. Then I can act with a single P. I can act with 2 of them. And so on. And okay, and let's see how do these things transform under D and M. So we said that this one has scaling dimension delta. This one has scaling dimension delta plus 1. This one has scaling dimension delta plus 2, and so on. And let's imagine that this A, well, the A index, it's some irreducible representation of SOD. So let's call it representation rho. So rho is a finite dimensional irrep of SOD. I mean, these are of course classified. They're classified basically by Young tableaus. Then, so we have finite dimensional vector space of scaling dimension delta. Then we act on it with the raising operator. The raising operator itself transforms like a vector of SOD. So here we get rho times the vector, which is usually denoted as the single box. So don't worry if you don't know this notation, but there is a classification of arrays of SOD, which is in terms of the boxes, and the box means the d-dimensional fundamental. And this is d plus 2 rho times the symmetric squared of the box. Okay. Okay. Questions? I mean, maybe this was a bit fast, but yeah. This is what? Yeah. Okay. So let me explain it a bit better. I mean, this. Sorry. So, okay, I'm erasing the hermiticity conditions. Right. So we are trying to construct representations of the algebra, and we want to start it by starting with some lowest weight vectors and applying raising operators to them. And now the lowest weight vectors, they are themselves a representation of a subalgebra, which is this SO2 plus SOD, generated by D and MAB. Okay, so first of all, we should pick an irreducible representation of SO2 times SOD. That's going to be our set of lowest weight vectors. I mean, irreducible representation of SO2 is just one-dimensional, and it's labeled by the number delta. And so, delta. So it just means that D acting on our vector is delta times the vector. An irreducible representation of SOD is what we call rho. So I guess that means that there is some finite dimensional space of these guys, and when MAB acts on our thing, then well, I guess there's a rho. How do we write this? So I guess so. MAB for fixed AB is going to be some matrix. So let's see. A runs from 1 to dimension of this row, and MAB is represented by matrix right. So there is some matrix of size dim rho, such that this is the representation of rotations in that particular representation. And so, for example, for the fundamental, it's just a bunch of Kronecker deltas. It's SOD representation theory. And then when we act with the raising operators, we just raise the scaling dimension by 1 every time and make the SOD representation a little bit more complicated, but in a way that we understand. It's just adding tensoring with symmetric representation. Okay. Okay. More questions? Yes. Mm-hmm.
The same as saying that, as you said, that we can always find the basis in which is diagonal.
Mm-hmm. Yeah, it's like a general fact about unitary representations that you can always diagonalize all the operators. So the question is why can we always find a basis?
Why a state which is represented by K is also negative to B? But if we can always find a basis in which D is diagonal, I can understand it, but now I cannot understand why we can
You cannot understand why?
Why we can always find a basis in which D is diagonal.
Where D is diagonal. So I'm not sure if it's... Well, yeah. If you're in a finite dimensional vector space, then it's obvious. But this is not a finite dimensional vector space. Yeah. Okay. I agree. It's not. Okay. I'm not. I don't remember the argument. Yeah. I think it depends on the fact that D is Hermitian in an essential way. But okay. Yeah. I don't. I guess maybe that's enough. Just the fact that D is Hermitian. But I can't give you the complete answer. Oh, so what time did we start? At 4? Okay, then let's take a break, like for 5 minutes. Okay, since I got some questions about the derivation during the break, let me just summarize. Maybe there was some point where my notation was a bit inconsistent, but basically it's important to distinguish mentally between geometric transformations, which I was originally denoting by these little lowercase letters, okay, and so on. And so these are the vector fields. And the quantum operators. So these are the operators acting on our Hilbert space. And they are kind of completely different beasts. This is just some vector field on a cylinder, and this is a quantum operator acting on a Hilbert space. And it's then we ask which of these are Hermitian or anti-Hermitian, and they are those which come from real vector fields, and real being interpreted in the Lorentzian signature. Okay, so there's an important kind of mismatch between eyes, that real vector fields. So real vector field in the sense of vector field just being complex conjugate of itself becomes an anti-Hermitian operator. So if I promote V to a quantum operator, then V hat dagger is minus V hat. Okay, so if there's no minus and there's a minus. Okay, and real meaning real acting on the Lorentzian spacetime. So that was kind of an important point which I didn't emphasize because I was denoting the vector fields with capital letters, just like the quantum operators. Okay. Okay, so now let's put unitarity into even better use. I mean, in some sense, we already used unitarity because we assumed that D was Hermitian, and therefore it also has real eigenvalues, it's diagonalizable. But unitarity is stronger than that. So we have these representations. Let's call them. Well, I guess let's call it D. So the irreducible representations are labeled by delta and rho, where delta. So far delta is just a real number, and rho is an irrep of SOD. And the representation corresponding to these labels is this one. So maybe this one. Here's a basis for R delta rho. But it turns out that not all of these representations are actually unitary. Only some subset is unitary. And we are going to, so we still want to classify which delta and rho actually are unitary. So unitary means that there's an inner product such that those hermeticity conditions are true, the ones that we wrote down before. And let's do the simplest case first. So let's start with the lowest weight state. So okay, let's do the rho equals identity first. So rho is a trivial representation, the one-dimensional representation, which means that the lowest weight state, lowest weight space, is one-dimensional. It has single O, and we can. Okay, now we start talking about the inner product. So let's normalize the inner product in such a way that O, inner product O, is 1. And okay, and now let's go to level 1, where we have a bunch of states which are obtained by acting with the P on O. And we want to know their inner product. So first of all of these states are orthogonal with the lowest weight state because this thing vanishes. By the Hermitian conjugation, we can make this into a K, and K annihilates O, so we don't have to worry about that. But let's worry about the inner product of these D states at level 1. So that's the same thing using the fact that Hermitian conjugate of P is K. Is that okay? Now we can write this as a commutator because K annihilates O. And then we remember that commutator is equal to delta AB D plus M AB O. Now O transforms trivially under rotations. That's our assumption somewhere. I forgot where. Oh, here. So it's trivial, which means M annihilates it, so M goes away. And delta has eigenvalue D on O, so we just get 2 delta AB, 2 capital delta, little delta, AB. Okay. And, well, since this inner product needs to be positive inner product, it's only possible when delta itself is non-negative. Okay, so we have a constraint that unitarity implies that delta is non-negative, and in fact it can only be 0 if P annihilates O. Right, so if delta is 0, then the norm of each of these states vanishes. Assuming unitarity means that O is 0, and in this case the whole representation is one-dimensional. So the whole representation 0 trivial, so is just one-dimensional and generated by O. So it's basically something which doesn't, well, doesn't depend on where it is, and it can only be the identity operator. So it's the only operator which has a 0 dimension is the identity operator in a unitary theory. Okay, and now let's go to level 2. So now we want to compute the matrix of inner products of these states. Right, so let's consider PAPB acting on O, inner product PCPD acting on O. So that's O, K, A, K, B, P, PCPD. Okay. Now I can either do the calculation on a blackboard or leave it as an exercise, but maybe we are a little bit short on time, so let me just tell you the answer. I mean, it's some gymnastics of commutation relations, right? First you exchange these using commutation relation, then you end up with KP, KP, and then you use the commutation relation twice. It's pretty algorithmic. KA, KB. Well, they commute. K's commute with each other. It doesn't matter. So when the dust settles, you get this. For delta plus 1, delta AB, delta BC, plus delta AC, delta BD, minus delta AB, delta CD, yeah, that's it. Okay. So now, okay, it's some exercise, which this is exercise you should definitely do. Is it clear how to in principle do this exercise? Okay. Maybe some of you have already done some conformal field theory also. So, okay, but where do we go from here? We want to know. We want to make sure that no matter what state we prepare, so imagine we prepare a general state, meaning that we contract PAPB with some symmetric complex matrix, and we want to make sure that the norm is positive. So that means that we should multiply this by AB complex conjugate, ACD, and ensure that this is positive. Now, it turns out that there is a kind of a, okay, and this seems like a maybe somewhat non-trivial problem, how to make sure that this is always positive. There is a trick, which is to basically to decompose this matrix into its, sorry. So first of all, the matrix is symmetric without loss of generality. Right, the matrix multiplies PAPB, which is symmetric. I can take it to be symmetric. And then the trick is to decompose the matrix into its traceless part and the trace part. And when you do that, then you just need to, well, the right way to do it is to decompose this thing into its traceless part and the trace part. So let's, what's the traceless part? Well, if you have something like delta AD, sorry, let's define projectors. The projectors onto the traceless part, so let's call that 1, or maybe to be the symmetric traceless object, which is AD delta BC plus delta AC delta BD, but it should be traceless, so we need to do minus 2 over D delta AB delta CD, okay? And then the projector onto the trace itself is just delta A B delta CD, right? So the point is that this tensor is traceless when I contract with delta CD or delta AB, doesn't matter. So I've removed the trace. And now what I should do is to rewrite this inner product, this matrix of inner products, in terms of these projectors. So the matrix of inner products is KA, KB, PC, PD. It's obviously symmetric under AB and under CD, but it's not traceless. Instead, it's this, which is the same thing as 4 delta plus 1. And now this object is the same as this plus 2 over d times that. So it's the traceless one plus 2 over d times the trace. And then this is just the trace itself. So let's put the projectors together. So we have delta plus 1 times the projector onto symmetric traceless plus, so what is this? It's this times that, so it's 1 over d, 2 delta plus 2 minus d. A, B, C, D, 0. Sorry, my handwriting has deteriorated. Right, so now once we do this projection, the positivity is just the criterion that both of these coefficients are positive. Because we can decompose A into its traceless part and a trace part, and then you just get a square here and a square here. So the necessary and sufficient condition for positivity of the inner product of the norm is that individually these two coefficients are non-negative. We already know the first one is non-negative because delta is positive. So we need to worry about this one. So we have unitarity at level 2. Level just means number of PAs. Is equivalent to that being positive, which is the statement delta is greater than d minus 2 over 2. Well, or delta is 0, right? Because if delta is 0, then there's a 0 multiplying the whole thing, and the whole thing is non-negative, so it's fine. But we already dealt with this case. That's just the one-dimensional trivial representation, so let's forget about it. And okay, so here it gets something interesting because this number we have already met before is the scaling dimension of the free field. So we have learned that for any scalar, for any row trivial, it's called scalar representation because it doesn't transform under rotations. So any scalar representation needs to have a scaling dimension which is at least the one of the free field. And now but it can be equal to, right? So if it's equal to, then that means that, well, this part vanishes, which means that the trace part has a vanishing norm. So the norm of this state is 0, which in a unitary theory means that the state itself has to be 0. Right? The only way Yeah, the only way you can, basically the inner product needs to be not just negative but actually positive. If it's 0, then the state just not there. So this state has to be 0. And that's the same as the equation of motion, right? Because the PA of a local operator, okay, I haven't really spoken about it, but PA acts like the derivative. So this is, under the state operator map, this statement becomes a statement that the equation of motion, that O satisfies the equation of motion. So it actually has to be the free field. So this is kind of a completely representation theoretic interpretation of the equation of motion. Okay. Now it turns out that for trivial row, these are the sufficient. So if you can keep going to higher and higher level and repeat this exercise, and you will never find any new constraints on delta. This is not really obvious, but it can be done. There is a complete proof to all levels. So the representation delta 0 is unitary if and only if either delta is 0 or delta is greater than or equal to d minus 2 over 2. I mean, in this case, we have many null states. They're all the p acting on any number of times is a null state, and here every state which contains a contraction of PA with itself is a null state. Okay. Okay. Then, well, you can do this exercise for various other rows, right? So we would like to know when is this representation unitary for general row, and the answer is that it's unitary whenever delta is greater than or equal to some number. Let's call the number b for bound. The number depends on row, and actually this number can always be found just by looking at level 1. So for a row equals 0, we have to go to level 2. For a row which is not the trivial one, you can just work at level 1, and whatever you find is the necessary and sufficient condition. So for example, for a row being the symmetric traceless, of rank j, the condition is that delta is greater than or equal to j plus d minus 2. Yep. Uh-huh. Yes.
And then if I want a conformal scalar, let's say, I have delta equals to d minus 2 over 2, right?
That's, well, yeah, but that's a different usage of the word scalar that I'm using. I'm using the word scalar more generally, just for a local operator that's invariant under SOD, under rotations. So it doesn't have to be the free scalar. It can be, so for example, for me, phi phi, the normal order phi squared, is a scalar for me. Yeah, it has a dimension d minus 2, so not free, but it's a scalar. I mean, in the way I'm using the word scalar, which is the standard one in the for higher DCFT literature. Okay, if you wish, as an exercise, you can do this for j equal 1, for example. For j equal 1, well, you have OA So now this is the set of states at level 0, and if you go to level 1, you have to compute a matrix of inner products of these states. So you would do something like OA PB, KB, PC OD. Okay, this needs to, well, if you contract this with matrices, you need to be positive. Then you use the commutator. But now the commutator will have the scaling transformation, but also rotation. And the rotation will now be important because the rotation will not annihilate the O like it did for the scalar case. So that's how you're sensitive to the SOD representation of O. Anyway, the conclusion is this, and it's saturated for conserved currents only. So the delta equal to J plus D minus 2 can only happen, I mean, just like this saturation could only happen for O which satisfies the equation of motion. This saturation can only happen when, so we have an operator which is symmetric traceless of rank J. It can only happen when if this equation is true. So this is called conserved current. Now for J equal 1, you get that delta is D minus 2 plus 1, which is D minus 1. For J equal to 2, you get that delta must be equal to D, which can really only happen for the stress energy tensor. So stress energy tensor is the only allowed spin 2, so J equal to 2 conserved current. And indeed its dimension is D, as it should. So this is kind of a way how from unitary representations you can recover. You can start seeing the structure of a quantum field theory just by studying representations of a Lie algebra. That's already quite remarkable. Like, you know, I could have just started told you, well, here's SO2 comma D. It's some classical Lie algebra, and just from that, you would start seeing, D minus 2 over 2 equation of motion, conservation of currents, without ever putting any space-time into the picture, just from the group. Okay, so I want to do one more thing. Or maybe, are there any questions about this so far? I didn't tell you what the B is for general rho, and it's kind of messy. Yeah, I mean, you can ask for the free fermion, I guess. Sorry, for fermions, it's like delta must be greater than or equal to D minus 1 over 2, I think. So that's for the spinor representation. Yeah, sorry, there was a question.
Yeah, was this a question about why should unitarity contain information about symmetries?
Why should unitarity contain information about symmetries?
Because like, you put conserved colors, right? You put conserved colors that have symmetries.
Ah, I see, in that sense. Well, sorry, so I guess unitarity allows you to prove the converse. So if you, without unitarity, if you have a conserved current, you can conclude that the dimension of the conserved current has to be D minus 1, just from the word identity, right? Because you have like this, when it acts on some local operator, is going to contain the delta function x minus y and the change of the local operator under the symmetry. Just from this kind of equation, you can conclude that delta has to be d minus 1. But unitarity allows you to go in the converse direction. It allows you to say, if you have a spin 1, like a vector operator, vector field, which has a dimension, which has this dimension, then it has to be conserved necessarily. Yeah. Mm-hmm. Yes. Ah, yeah, that's a good point. Why is it? Yeah, I mean, you're absolutely right, but there's a subtlety, and I don't remember what was the subtlety. Okay. Well, but remember, at level 1, we found just this, right? This was the level 1 constraint for the scalar. So why does this not agree with that for j equals 0? I mean, I'm sure it's fine. The equations are correct, but okay, I don't remember. I guess we. Why is it? I think maybe it has to do with the traceless. I think some other traceless number with 0 indices. Like j equals 0 is really just a symmetric number with no indices. But once you remove the trace, maybe you're gonna get in trouble. So, yeah, the answer is just do the calculation for 0j and do the calculation for non-zero j, and you will see that the answer for 0j is not the analytic continuation of the non-zero j answer to j equals 0, but I can't tell you exactly why that analytic continuation fails. Yeah, that's you guys are asking some good questions. Especially today, I'm feeling. Okay, so we were talking about states the whole time. So now let's just bring it back to the operators. So the point is that, okay, well, first some terminology. So the lowest weight state so what I was calling O, it's called primary. That's just the name, and then the higher weights. So the states like obtained with some finite number of the momenta, they are called descendants for kind of obvious reasons. They are descendants of the primary. And the same terminology then transfers to the local operators under the state operator map. So the primary under the state operator map corresponds to inserting a primary operator at the origin. So it's a local operator at the origin. And the descendants they map to the derivatives of the local operator at the origin. Yeah, so but it's also good to be able to talk about local operators away from the origin. But now it's easy because I mean a local operator at some position x can always be Taylor expanded using the derivatives. Right, so the way to think about it is that if we want to insert an operator at x, we can conjugate it with translations. Right, so we start with the operator at the origin, and we conjugate it by translation. This is how symmetries work. And now we can ask, how do the conformal generators act on O of x? So we already know that PA, when it acts, so now I'm kind of freely going between these different pictures of the Euclidean QFT and the Hilbert space QFT. So by this, I mean now the view of P as a charge, thought of as a topological codimension 1 defect, right? So we have an operator at x, and we surround it by a topological defect, which corresponds to one of the charges, the P, D, K, and M. So let me just do the scalar case. So rho is trivial, and I'm just going to write it, and then we can go home. So this is just the derivative, right? Sorry, maybe I should say how do you derive this? So this, in the Hilbert space picture, becomes the commutator. Okay, I should probably use different notation. So this, in a Hilbert space picture, is the same thing as taking the quantum operator acting on a Hilbert space and commuting it with it, right? Because kind of if you're say on the cylinder, then you can deform this operator from the top and the bottom. So you basically have the charge at the top or charge at the bottom minus the. So it's the usual story of how action of symmetries by topological defects becomes a commutator. So if you do the commutator of P with this expression, you'll find just the derivative. Now, if you do it with D, then you'll find this. So notice how it's slightly different from the original vector field because there is this extra factor of D, delta. If you act with the rotation, then you get just the vector field. This would be different if we had been working with a non-scalar operator.